Okay, the latest one I was able to open. So that's good. Okay, so you probably, both of you, have the same question because you guys were both gone at the beginning of the class. And we had 3 quizzes in the first week or 2 while you were gone. We haven't done many quizzes since. But the first quiz, the introduction quiz, is pretty simple. I just want you to send me an email that tells me your name, what kind of engineering you're interested in going into, and I think that's about it. I just wanted to know some more about you guys, so just send me a quick email that'll satisfy that. That way I can enter it into my records. The video quiz was kind of an assignment / a quiz where I asked everybody to go out and watch 30 minutes worth of videos about engineering. It could be 1 video or 2 or 3 videos, but it needs to be at least 30 minutes worth of videos about engineering, and write a 1-page or less description of the videos that you watched, what you learned about. Yeah, resend that, because go ahead and resend that if you did that. It very well could have gotten lost. We had a lot of things that we weren't able to open in the beginning. And then the first quiz, I'd have to go back and look at my papers to see what that was. I can't remember exactly what that was, but I will do that. Now that I can see this on this latest email, looks like that was sent today. So, yeah, now that I can see that, I should be able to go back and figure that out for you. So. All right, now on our schedule it says that we're going to do the motor project for 4 class days, but I don't think we're going to spend that much time on it. You guys are understanding how to do projects fairly well. I'd like to speed up this next project. The project is really quite a simple one. Today we're going to spend some time learning about how electric motors work, and then you are going to design and build and test your own electric motor. I do believe that your kit came with some wire in it, some copper wire. Do you remember seeing copper wire in your building kit? Are there magnets in there as well? Okay. So those are the things that you definitely need. You'll also need a battery, and I want the motor that you design to work off of a battery that is 9 volts or smaller, and a household battery, not like a car battery or a motorcycle battery. So a small household battery you can use. The biggest one you're allowed to use is the square 9-volt battery, but you could also use a D-size battery or a AA or whatever, C-size. The 9-volt will give you the best. So, but it's just kind of up to you when you build your design and you start testing it what you want to use. And you're going to do the same thing. You're going to keep a logbook. You're going to track all of your work. But instead of this going for starting today all the way until next Friday, I'd like to be done with this by Monday or Wednesday at the latest. Have it designed, built, and tested. It shouldn't take that long. It's not terribly mechanically difficult to build or design. The most difficult thing about motors really is the placement of certain components so that they actually spin properly. But that is the next project, and today we will learn a little bit about how motors work so that you can understand how to go about doing this project. And then we have, if we can get this done by Monday, that would be great, because we actually have 2 hydraulic arm projects. We have one where we're going to build a simple hydraulic arm, and one we're going to build articulating hydraulic arm that can have a lot of different movements in it. And this is probably the most technically and mechanically challenging project that we do this entire semester. After we're done with that, we will move on to our three-dimensional drawing settings portion of the class and do some 3D prototyping of some designs. And then we are done with this class. Notice that we don't have any more exams really scheduled. We have the final, during the final week of the course we will have what we call a final, but that will essentially just be a presentation. And so make sure that you're keeping very good logbooks from here on out of all of your projects, because you will need that information of these projects to do your final presentation. And of course you will always turn in your logbooks at the end of each project as well. Any questions about where we're going today? Okay, so let's learn some things about electric motors. Actually, electric motors work on a principle that was discovered and worked out in the 1800s by several different scientists. We're going to look for simulation here really quick. And this thing the thing that they discovered back in those days was, where am I looking here? Oh, here we go. One of the things that they discovered back in those days, hopefully this works, is that when you have a changing electric, when you have a moving electrons or changing electric conditions, it creates magnetic conditions. And I'm not getting a picture up here for this. Dang it. Sorry, this computer is not working. I'm going to go grab another computer. I'll be right back. Alright, let's try this again here. Switch to this computer and try to make it work. Yes? Okay, I'll try to fix it here really quick. Did that change anything? Not really. Okay, is that bigger now? Okay. Alright, so let's see if we can make this work here. Oh, come on. This must not be, the website must not be up to date with its Java stuff either. This is kind of obnoxious. I suppose I can do this without having animation. We'll just go ahead and do that for the moment. The first discovery made one of the first discoveries made with electricity and magnetism is called Lenz's law. And essentially what they learned was, let me find a good picture of this here. Here's a good picture of it. What they learned was that if you have a wire that's carrying electricity, or in other words, moving charges, moving electrical charges, it creates a magnetic field around those moving electric charges. So if this is a wire, you get this magnetic field that goes around in circles around the wire. And what they discovered later on was that it was the fact that the electric field from the charges was changing because they were moving through space. And that led to a law that's called Faraday's law. And laws in physics and science are nothing more than observations. When you have a law, essentially it's something, a law is something that is always observed to be true. Well, it's always observed to occur. And so here is where this led Faraday, show here. Here we have a magnetic field, and here we have a loop of wire that's partially in the field. And if this loop of wire is it's really just a loop of wire, there's nothing connected to it. But if we move the loop of wire in the field, into the field or out of the field, it actually makes the electrons in the wire move. So in one case you have moving electrons that create a magnetic field. In the other case, you have a changing magnetic field going through a loop that creates a current or creates moving charges. It's kind of like they're kind of like opposites of each other. And it turned out to be one of the most important discoveries for mankind, because this led to the production of electricity, and it also led to the, how come I can't close this thing? Go away. It led to the production of electricity, and it also led to the use of electricity to do work with a motor. Well, how did it work? Well, it has everything to do with motion. As you have a loop of wire, or a circuit, that goes into motion, so here is a loop of wire, and if it goes in motion near a magnetic field, or if the magnetic field goes in motion near the wire, one or the other, it doesn't matter which, you will get a current that is going in the wire while that motion is occurring, while the magnetic field is changing nearby. And it doesn't necessarily have to be with motion. You can change the magnetic field some other way, and some motors take advantage of that. But it's the motion, but it's this change in the magnetic field near the wire, or through the wire, through the loop, that creates the current in the wire. And motors take advantage of this to cause spinning. Let's see if my Java download can be activated. Hopefully we can make this work. Because to really understand how a motor works, you really need to see it moving. So what this really means is, this combination of these two laws, is it means that every time you have moving charges, moving electrons, moving protons, moving anything that's a charge, if it's moving, it will create a magnetic field. If it's changing, and moving charges essentially amount to changing electric field. So changing electric field causes a magnetic field. It creates a magnetic field. And vice versa, changing magnetic fields near conductors or near wires, particularly wires that have a loop to them, loop going on in them, that creates a current in the loop. Let's see if this is working now. Oh, it says it's not working still. Isn't that great? Oh, let's restart this. How do you restart this? Start. Let's just quit. Maybe it'll work in Safari. I doubt it. I doubt it. Let's try anything. Let's make anything work. Will anything work? That one worked. Why did that one work? This one didn't work. Come on, work for me, Arthur. That's a good sign. Maybe. Dang it. Oh, I guess we can't just get in. That's just not going to work for us. Let's go to a different one here. Okay, so here this one's working. So here you can see the charge is moving downward through, these are the electrons, they're moving downward through the wire, which results in kind of an upward movement of positive charges, since electrons are negative charges. It's not really an upward movement, but it's close enough. And then you have this magnetic field that's being created up here. They put a little compass down on this table to show you that 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 magnetic field that's happening. And if we change the current through this, so if I go up here and reverse the current, it's going the other way, it actually changes the direction of the magnetic field. Instead of going, if we were looking down on this, instead of going counterclockwise, now it's going clockwise. And what happens to the compass? Well, it switches direction. And this is actually a very simple motor. If you change the direction of the current going through here, you change the direction of the compass. And if you switch this going back and forth very quickly, you would get the compass moving back and forth very quickly because of this effect that changing an electric current changes the magnetic field, and changing magnetic field changes electric current. So, how do we take advantage of this in a motor? So this is a very simple motor. It's what is called a direct current motor, which means it's run by something like a battery, where the current is always going one direction. And that's represented over here by these wires with the positive and the negative connection right here. This is where your battery would connect right here with the positive terminal here and the negative terminal here. And we have this thing that these things that are connected to the battery, these are called brushes. And then we have this rotating disc in here, which is called a commutator. The red part of the commutator, which turns gray every once in a while, so these little two almost half circle discs, those are made of metal, and this little black stripe down the middle is actually made of something that is non-conducting, plastic or wood or something that's not a metal, essentially. Each one of these commutators is then connected to a wire that goes around in a loop and then connects to the other side of the commutator. And then we put the whole thing inside this big U-shaped magnet, where we have the green side of the magnet representing either the north or the south pole, and the red representing the other. In this particular case, the north pole is going to be the red side, and the green pole is going to be the south side. The reason we know that is because, by convention, magnetic field lines always go from the north to the south pole, and so that's what we've got going down here. So this is how it's built. How does it work? Why is it doing what it's doing? Why is it rotating around? Well, it's really quite simple. What I'm going to do here is I'm going to pause this right here. At this point in the motor's motion, the brushes are in contact with the plastic, which means that they are not going to have any current flowing out of them or into them, because they're not connected to anything. There's no circuit here. For current to flow around a circuit, there has to be a connection to the circuit, and when the current gets to this top one, it sees plastic and it can't flow through plastic, and so nothing happens. And the magnetic field here, which is going from the north pole to the south pole, is going right through the middle of this loop, but the loop has nothing going through it, and so there's no interaction. Remember that in the first experiment we saw, when you put a current through the loop, it creates a magnetic field. And that is true with this loop as well. Like if you have it connected to a battery, and the battery actually drives current through this loop, you would have a magnetic field in that loop. And it turns out that the magnetic field in that loop will try to line up with the magnetic field from this magnet. But right now there is no magnetic field, so there's nothing going on. However, if we let it rotate a little bit, this is what will happen. Oops. So if I let it rotate just a little bit, notice that the brushes here are in contact now with the metal that is connected to the loop. So now we're driving some current through this loop. The current will go from the positive to the negative, so it's going along this top part and around this way. And you can see here that there are some black arrows here. Those black arrows represent force. Whoa, what's going on here? Oh, you gotta be kidding me. Okay, I'll be right back. Hold on a second, I gotta fix this. joking. Can't fix it. I'm going to go back to my other computer and see if I can run this again one more time from the other computer. No end to problems with this mess. Okay. I don't care. Go away later. So anyway, here we go. So, as the current goes through this wire, it creates a magnetic field around the wire, excuse me, and it turns out that that magnetic field that it's created will point perpendicular to the surface of the loop. So if you have a loop that is going around here like this, the magnetic field will either be coming out of the board or into the board. In this case, it's at this angle, so the magnetic field is upward or downward, and these force vectors are caused by the fact that that loop wants to rotate and line up with the magnetic field that it's in from this big magnet here. And so it tries to flip itself so that those two magnetic fields line up. That and the forces here are pushing this way and this way, which obviously means that the magnetic field is pointing upward, and it wants to point downward because this magnetic field is downward. And that is true. It's pointing upward and slightly into the board or into the screen as this current is going through it. How do you determine which way that magnetic field is pointing from the loop? We use what is called a right-hand rule. This is something that you may have learned about if you've taken physics, and if you haven't, you will learn about it someday. But we use a right-hand rule to help us determine which way this is going. And essentially, for any given loop, you take your right hand and curl your fingers around the loop in the direction of the current. I'm going to let this go a little bit longer so I can show you how this goes. So in this particular case, the loop is up on top, and you can see that there's an arrow. Maybe you can't, or maybe you can, but there's an arrow in the loop here going around. And that arrow is going to the right on the top of the loop and to the left on the bottom of the loop. So if I put my hand on the top of the loop and curl my fingers around towards the bottom of the loop, my thumb will be pointing into the board. And that thumb pointing into the board tells me which direction the magnetic field is pointing, which means it's into the board and slightly upward, because this is out of the board and slightly downward. So it's into the board and slightly upward, and the magnetic field from the magnets is pointing downward. So the magnetic field from the wire is trying to line up with the magnetic field in the magnet, and so it's trying to flip itself over. As it tries to flip itself over, it's obviously spinning, right? And that spinning is going to cause these brushes to come out of contact with these commutators again, these red half discs. Let's go on a little bit further here. And it gets out of contact right after this moment. Notice that it's not quite lined up with the field yet, so the forces are still trying to line it up with the field. The forces are still trying to twist this a little bit. But as soon as it gets lined up with the field, it's going to just stick there unless we turn off the current. And that's why we have this plastic thing in the middle, because we turn off the current right there so that the force will not stop the motor from going. And then when it's lined up with the field, we've turned off the forces, and it will just keep spinning because it's already spinning. But then as it keeps spinning, it comes in contact with the commutators. But we have switched sides now. Now this top brush is in contact with the commutator that used to be on the bottom. And the bottom brush is in contact with the commutator that used to be on the top. The commutators have switched positions, and so now the force starts all over again. The force, this force, or this magnetic field that's created by the current in the loop of wire, is now pointing upward again because it rotated all the way around. And so it's going to try to line up again. It tries to line up again, and it flips this thing around. Just as it lines up, we turn off the current, we switch the direction again, and we put it out of alignment again, and we keep going around and around and around. So every time it flips around, we switch sides with the commutators and the brushes. We create a new current that creates these new forces that force this loop of wire to try to rotate around again, and it just keeps doing it forever and ever, and rotates and rotates and rotates and rotates. Getting the positioning of this loop with the angles of this commutator are really the challenge in making a motor work. And you have to really think it through. When I'm lined up, when I'm not connected, I want this loop to be flat between my magnetic field, in my magnetic field. So that's when I'm lined up right on the non-conductor right there. You can see that. It's a really good idea to use one of these applets online. You just Google motor applet, and to use one of these motor applets to kind of get a feel for how you're going to design your motor. Also, there are a lot of websites out there, a lot of people that make electric motors at home that'll give you some key pointers and some design ideas and some tricks and tips for making it work right. But this is the basic idea of motors. You're constantly creating a magnetic field in a wire, then turning it off when it lines up with the magnetic field of the magnets, turning it back on again to make it flip around and line up again, and turning it back off again and turning it back on again, and so on and so forth. Now, your motor does not necessarily need to be just like this. And obviously it couldn't be. This doesn't really show you, for example, how the brushes are connected to this thing and how you keep them close to this thing. It doesn't show you how this thing is rotating. It looks like here it's just levitated in free space, right? You're going to have to figure out some way to build a frame, some kind of rotating axis, some kind of thing to hold these brushes. You're going to have to figure out what you're going to make the brushes out of. We're going to have to figure out what you're going to make the commutators out of. And you have lots of different tools and things in your kit that you can use to do that, to figure those things out. Also, the orientation of this motor is horizontal. It's rotating in a horizontal mode. That's not necessarily a design constraint. You can rotate it any way you want. Figure out something that works for you. I can tell you right now that this is not the easiest way to make a motor horizontally. The easiest way is certainly different. I'll let you think about that. But anyway, this is the idea of this next project, is to take these concepts of currents flowing through wires, creating magnetic fields lining up together, the changing of this direction of the current as the commutator rotates around with the brushes, and design a motor. Research, of course, you're going to have to do lots of research. Then design a motor. I don't want you to just take a motor that you find online and copy and paste it. I don't mind if you take design ideas from other people, but I do want you to come up with a design that is at least in part your own. And then to go ahead and start building this motor. I would ask that you refrain from adding anything to the kit. That means, I think that I gave you some pretty small magnets. That means that you're going to have to make a fairly small motor, because the motor, the magnetic field, is going to determine how big your motor can be. Well, a few things determine that. The current that you put through the loop, the size of the magnets, the size of the loop itself. The loop should be about the size of the magnets. If your magnets can slip through your loop easily, but not without too much room, then usually it's the right size, and you can even make them the same shape as the magnets. But there's one more thing that you should consider. If one loop can create a certain amount of force, two loops can create twice as much force. So you can loop this around and then go around again before you connect it to the commutator. Or you can do it 3 or 4 times or 50 times, and you would get more force. But what's the trade-off? As you add more wire, you add more right? So there is a balance somewhere. This is kind of like the trebuchet project where adjusting the arm length and the seam length and the mass and everything can have different effects. Sometimes it's a good effect, sometimes it's not so good an effect. So you need to decide how many loops you think would be ideal by doing a little bit of research, reading what other people have done. And then you're going to have to put that into your design, but I would also make it an option for you to change. Maybe make 3 or 4 different loops that have different number of loops in them, and trade them out of your motor. Or you can make 3 or 4 different motors with different numbers of loops. But certainly you need to take those considerations into account. Make sure that when you're designing your motor that you try to get your magnets as close to the motor as possible, because the further they are away, the more the magnetic field spreads out and you lose that magnetic force. And besides that, I'm going to let you go to do your next project. This project is a little bit of a challenge because you probably haven't had as much education in electronics and magnetism, and you certainly don't have as much intuition for electricity and magnetism. Most people don't. Most human beings have very little intuition for how these things work. So the research end of this project is going to be paramount. It's going to be important. You're going to have to learn as much as you can. I would highly recommend watching a few YouTube videos about electric motors and how they work. There's some really good ones out there, so that you can understand in more detail and have a little bit more depth of knowledge. And engineers have to do this all the time. They're given a project where they don't know everything. They're not necessarily experts on everything in the project, so they have to go out and become experts on the subject. So this is your opportunity to go and do that. You have any questions? Okay, we're off and running on the next project. Let's try to bang this one out as quickly as we can. On Monday, I would expect that you should be, we're going to follow the same format as we always have. Give yourself some time to do some research, start building up alternatives, evaluate alternatives, go through the process of creating a final design. Make sure that you have drawings and pictures and diagrams and everything that explain your thought process and your design process. And then as soon as you've got a good final design, start figuring out how you're going to build that and test it and get it done. Like I said, I'd like to see where we're at on Monday, and maybe be done with this by Wednesday. If we're done by Wednesday, we can start our next project and be ahead of the game. So have a good weekend, and if you have any questions, feel free to contact me.